Okay, happy day and welcome. Today what we're going to be doing is we're going to be doing a quick review of intermolecular force notes. We're going to be just kind of going through and trying to figure out like what are these IMFs and really just getting the main idea about what they are before we get into the details that we kind of need to do for AP. Okay, so they're weak forces. They're very, very weak. So when you think of like bonding, for example, these are not bonds, even though you're going to see that one of them is called a bond. But they're not actually bonds. So these are weak forces. And anybody know where they are? Are they inside the molecules or are they between the molecules? They are between. Awesome. So when we say inter, this word, this prefix inter, we're actually talking about when something is in between. Okay. So if we're talking about in between, what does that look like? So if I have a water molecule, we're going to draw a water molecule pretty quick right here. Okay, that's my water molecule. Don't forget, these are bonds on the inside. If I have another water molecule that's close by, and I am intentionally going to put the O over here. It doesn't matter where my H's go. I'll just draw them down, but it doesn't really matter where the H's go. They could have been up, okay? And so now what's going to happen is there's going to be an attraction. And the attraction is going to be between 2 points. We know that what attracts each other? Do opposites attract or like charges attract? Opposites attract, likes repel, right? So what's going to happen is we know that oxygen is a -2 charge, but it's bonded to these hydrogens. Water isn't an ionic compound, so it doesn't have a straight -2 charge. So what we say that water is a what kind of molecule? Polar. Awesome. Very good. It's a polar molecule. So what's going to happen is there's going to be a dipole moment. Which one's more electronegative, the oxygen or the hydrogen? Well, who's closer to fluorine? We know oxygen's a lot closer. There's going to be a dipole moment that's going to pull toward the oxygen. And when that dipole moment pulls toward the oxygen, when it pulls toward the oxygen, it actually is going to create a partial negative charge on the oxygen. And then the hydrogen is going to have a partial positive then. Well, the same thing is going to happen on this other water molecule. So this one, there's going to be arrows pointing, the dipole moments, pointing toward the oxygen again. And now we're going to have a negative charge that's right there on the oxygen. And again, the positives on the hydrogen. Well, what happens is this right here, this positive and negative between this hydrogen and this oxygen, create what we call the IMF. That's the intermolecular force. So I just kind of put dots right between them. I'm going to do one more so it's more clear without all the arrows showing up on there. So let's do one more water molecule here. I'm just going to add an oxygen with another hydrogen here. And then I'm going to throw 3 dots in between. And that is my IMF. Okay. A very weak force. And then we're going to talk about the types of IMFs in just a second here. Okay. So intermolecular forces are the forces of attraction between 2 or more molecules. Perfect. IMFs are different from bonds. Generally, bonds are within a molecule. And when they are within, anybody want to guess? They don't call them inter, they call them intra. Awesome. So that would be intramolecular instead. Whereas IMFs are going to be where? Between. Okay, intermolecular bonds may be broken when enough what is applied? Energy. Awesome. So we know that we're going to need energy applied in order for that to happen. Certain substances have weak forces and others are going to have strong forces. Therefore, IMFs are going to determine how high the melting and the boiling points are. They're also called, this is important, they also can be called attractive forces. They also can be called van der Waals forces. I want you to just say it. So everybody say van der Waals. Van der Waals, and everybody say attractive forces. Attractive forces. Those are going to be the same as IMFs. Okay. Under here, I want you to write this down. I want you to say that the reason why. So if I asked, or a kid asked, I was one of those very curious kids. So my mom said that she called me a but why kid. I don't know if you understood what I just said, but she was like, you're a but why kid. I was like, a but why? What do you mean but why? So when I was like getting older, I was like, I don't know what you're talking about. She was like, everything was always but why? But why? So it was like, Mom, how come like the sky is blue? Blah, blah, blah. But why? I always like wanted to know more. And so the question that you could ask a little kid too is, and get them thinking, is like, Why do some things exist in solid and some things in liquid and something in gas states? Well, it's very, very hard to actually describe or make get a child to understand, because anybody want to know? Give me those 3 letters. What is it all based on? It's all based on IMFs. Okay, so the phases of matter that something's in at room temperature is all based on the IMFs, the intermolecular forces between the molecules. So whether something is solid, liquid, or gas, all depends on obviously the temperature that it's at, right? But if they're all at the same temperature, IMFs, and then like a bunch of exclamation points so we don't forget that. Okay, so that's really an important part of this. Okay, so we already know about polarity. So there are 3 types of molecules. We've got nonpolar, polar, and then our ionic ones. So we know that nonpolar are sharing how? Electrons are shared equally. Then we've got polar covalent, and these are not shared equally. So they are sharing, but they're just not shared equally. And then ionics are not really molecules, right? They're either ionic or they're molecular, so they're not really molecules. And these are typically made of metals and nonmetals, or we can say cations with a positive charge and anions with a negative charge. And they give and take electrons, so they do not share. There is no sharing of the electrons. Polar bear analogy, I always like to say that you get 2 polar bears and you put food between them and they're like, "Rah!" Who's going to get more? The bigger one, okay? The one that has a higher electronegativity, okay? Polar bears do not share equally. So the more electroneg is going to have a partial negative charge. Will be partially negative. Okay, non-polar bears do share equally. Okay, those do share equally, and these typically are going to have everything's going to be equal going around it. Okay. Now, there's one thing that I want to make sure that we talk about. Actually, I think we're going to talk about it at the end here, is polar bonds versus polar molecules, right? Because there's going to be a difference between if it's a bond or a molecule. So we'll get to that in just a second. Before we discuss each type of force, you need to know what a dipole is. We already talked about this. So if this is water, what do you think the one in the middle is? Oxygen, perfect. So that's our O, those are our H's, and again, we just draw an arrow toward the more electronegative oxygen in that case. Now, there is an overall molecule dipole, and that is going to be, since they're both, the 2 vectors are pointing in the up direction and nothing's canceling out, you're going to get an overall vector going in the up direction. Okay, and then that is what makes your molecule polar. So this would be representing the polar molecule. These 2 would be representing the dipole moments. Okay, but again, that's still the dipole moment overall. Notice that the electrons are shared, but they're not shared equally. So you can see here that we've got these are being shared. And don't forget, it's not like they just stick there in the middle. The electrons are actually moving around, but typically you're going to get 2 electrons that are between the hydrogen and the oxygen in each situation. Okay, so the electrons are being shared, but they're not shared equally. And then not equally. Oxygen has a greater attraction for electrons, so the arrow points toward the oxygen, and then we already drew the dipoles. Okay, let's come down here. Okay, London dispersion. So everybody say London dispersion forces. London dispersion forces. So sometimes they call them induced dipole, but I've seen them either as dispersion or London dispersion. These are going to be the weakest of all of them. These are going to be the weakest. Okay. The London dispersion forces are for all molecules. All molecules, that's one thing about them. Okay, so if you're asked, which of the following will experience London dispersion forces? And you're like, oh, well, that one's hydrogen bonding, and that one has dipole, it's got to have London dispersion. London dispersion is for all molecules, okay? But it is specific to what type of molecule? Nonpolar. Awesome. Specific to nonpolar, not bonds, but molecules. Well, a nonpolar bond is going to be a nonpolar molecule. Okay, so for example, if you remember, if we were to draw something like carbon dioxide, CO2, do you remember what carbon dioxide looks like? 2 double bonds on either side. So we're going to get a C, double bond O, double bond O. Polar or nonpolar? Nonpolar. So this would be an example of a London dispersion force because this molecule is considered nonpolar. Okay, the dipole moments will cancel out, and the only thing that you're going to have are these weak forces. I'm going to show you on the next page a little bit more of what those look like. Dipole are going to be stronger than these. And these are specific to, anybody want to guess? Polar, awesome. Specific to polar molecules. Okay, and so, like for example, anybody remember what NH3 looks like? What the shape will be for NH3 for ammonia? Trigonal pyramidal. Awesome, trigonal pyramidal. So you're going to have an N on top, and then you're going to have H, H, and H. Something like this would be a polar molecule. Now, if it was trigonal planar, it would be nonpolar. Okay, but if it's, for the most part, but if it's like that, then that's going to be a polar molecule. Now, the only thing with this, and so sometimes I like to change this up because for a reason. So what I'm going to do is, I know that's NH3. I'm going to actually change my H's, and I'm going to make them, let's make them, I don't know, F's. We can make them F's instead, and it'll still take on the same shape. Okay, so I'm going to make this an F. I'm going to make this an F. You're going to see why in a second here. And I'm going to make this an F. Okay. And now, these are the strongest of the three, but, with a disclaimer, hydrogen bonding is only, anybody want to guess at the strength of a hydrogen bond to a covalent bond? To an actual, like, this kind of bond? Yes, good. 10%. The strength of a covalent bond. Okay, so even though it's the strongest of these, it's still very weak. Okay, which is why, oh, let's finish this off. Okay, so these are specific to polar molecules. What about hydrogen bonding? It's also polar molecules, but it's a special case. With a special case. Anybody remember what hydrogen bonding is specific to? You can say it. Nice. I always like to say phone because it's easy to remember. So it's H with F, O, or N, which is why I just changed that to NF3 because now we're going to write NH3. So N, H, H, H. That can be our example for hydrogen bonding. Okay, and don't forget, it's not inside of the molecule, it's between two molecules. Okay, so these are covalent bonds that are inside. We're talking about between two of those. Okay, all right, let's flip. Okay, this is going to go pretty quick. This is showing London dispersion forces. They're temporary dipoles. The electrons are going to move around. All atoms contain electrons, so they all must have London dispersion forces. Okay, and this is the weakest type of IMF. If you take a look at frame 1 versus frame 2 versus frame 3, we have helium, just helium, and it's supposed to be like at 3 moments in time. Okay, but what's going to happen here is, first, we have the nucleus, which we know is charged positive, and the electrons are charged negative. Then in this frame, the electrons are just moving, right? Because the electrons don't stay in one place. What happens in this frame is our negative electrons actually end up together on this side, creating a partial positive, a partial negative charge, meaning that this side ends up taking on a partial positive charge. And when that happens between two helium atoms, you get a very temporary dipole, and so that temporary dipole is called the London dispersion force, but it just comes and goes. It's very quick, so it doesn't really stay, okay? That just explains how you get that partial positive and negative, but it's not making it polar. It's not a dipole moment per se, it's just very temporary. Okay, So now let's take a look here, and we have the atoms or molecules. Oh, this is just showing, again, this spreads throughout the material, possibly turning a gas into, what could a gas turn into? A liquid, yep. Or it could possibly turn into a solid, depending on how close those are, but typically not. That's why usually your nonpolar molecules are in what phase at room temperature? They're usually what phase at room temperature, the nonpolar molecules? They're usually going to be gases. Okay, they're usually going to be gases. All right, and so that's just showing that, again, where you get two, where your positive nucleus and your negative electrons end up connecting, and so that is called your LD force. Okay, that's your weak IMF, your LD force. Okay, so it says the strength of an induced dipole is actually proportional to the number of electrons that an atom or a molecule has. This is interesting. So a lot of times when we look at something, and the AP is going to be very intentional about this, College Board is going to be very intentional about this, they don't actually want you to say that it's according to its molecular mass. They want you to describe why. It is true that the bigger the molecule is, the more the stronger your LD forces are going to be. So if you're comparing three and they're all nonpolar, and there's nothing else that you can say about them in order to compare them and say which one's stronger, and you're like, they all have London dispersion forces. I don't know, what am I supposed to say? You actually want to use the molecular mass, but it's really the number of electrons that we're really focusing on. Okay. What this is called, and I want you to write this in like really big letters, it's called, and it's going to come up again, it's called the polarizability. This is a very fun word. Everybody say polarizability. Polarizability. I love this word. Okay. So we're seeing like the word polar in there, and then we're seeing ability. So what are we talking about here? The ability to become polar. Okay. The ability for something to act like it's polar is the polarizability. So the ability to act like a polar bear that's not going to share equally, right? So what happens is, the more electrons that you get, the more movement of the electrons, right? And it basically creates this like squashiness is the way that I refer to it as. So we're going to say it's like the squashiness of the molecule, how squishy it is, okay? And so the more electrons that you can get, the more attractions you can have. Okay, and so the polarizability, we're going to end up defining it when we do our notes to the AP set of notes, but I just wanted to bring that up here because it is molecular mass, but it's really supposed to be based on the number of electrons. Okay, but the molecular mass is going to be the giveaway on whether, that's how you're going to be able to tell pretty quickly which one has stronger LD forces, okay, if it's only LD forces. Okay, so if it had dipole, then that's stronger than LD, right? So we take a look here at the noble gases, for example, and we can see that the molecular weights, 4, 20, 30, 40, and then 84, what happens to the boiling points as the molecular weight increases? So as you go down, the molecular weight is increasing, and as you go down here, what's happening to the boiling point? The boiling point is also increasing. Boiling point is a really nice way to figure out IMFs, how strong the IMFs are. Because what you do is you just heat them up, right? And the ones that actually boil the fastest must have what forces? Weaker or stronger if they boil first? Weaker. You were able to break them apart faster, right? So the faster that you can get them to boil, or the lower temperature that you can get them to boil, if their boiling point's lower, then you know that those actually have weaker forces. So the higher boiling point actually indicates the stronger LD force. Again, IMFs, but these are the noble gases. Noble gases aren't sharing electrons, right? So those are going to be, so as the molar mass increases, the boiling point also increases. But again, molecular weight's not your accepted explanation. We want to use polarizability. And I've had students actually look for like where they can use the word. They're like excited to use the word polarizability. Okay, all right, let's take a look at the next part now. Okay, so, and let's pause here actually for a second before we take a look at the other two types. So now we've got dipole. These are permanent dipoles. And so it says polar molecules have a net separation of charge. HCl is a really good example. like H2O, but there's a reason why I'm not using H2O. So the positive and negative are attracted to one another, which is why we call it a dipole, and I'm going to show you right now why. So if this is H and Cl, so I've got an H here and I have a Cl here, and then I also have an H here and a Cl here, then what's going to happen is my partial negative on my chloride is going to be attracted to the partial positive on this. Well, there's a dipole moment going this way, and there's another dipole moment going this way, which is why they call it dipole. It's two dipoles that have created this. Great question I always get asked. Could you actually have two different things still have a dipole moment? Yes, you can. Okay, so that does happen with those polar molecules. Okay, hydrogen bonding, it's a special form. So we said that it's with fluorine, oxygen, or nitrogen. So I like to say phone, F-O-N. Atoms in, okay, there's a strong attraction between H atoms in one molecule and then one of those in another molecule. So just remembering that it's two separate molecules. Hydrogen bonds are the strongest type of IMF, but remember what we said, it's only 10% of an intramolecular covalent bond. Water is very polar, it has forces, water is going to have all three. It's going to have London, it's going to have dipole-dipole, and it's going to have hydrogen bonding. So if it has hydrogen bonding, it's got to have all three of them. If we take a look at these pictures, we can see there's our hydrogen bond there. There's our hydrogen bond in between there. We've got some cytosine and some guanine for our bio lovers down here. So we've got hydrogen bonding between the oxygen and the hydrogen, the nitrogen, and then again, the oxygen and the hydrogen. This is what I wanted to show you where there's also a hydrogen bond going on there. Some examples of hydrogen bond, we know again, it's hydrogen with F, O, or N. Okay. And there is another type, and it's called ion dipole, and I'll talk to you about ion dipole. Actually, we'll take a look and see in just a second here. So hydrogen bonding greatly increases boiling points. If we take a look at the boiling points, if you didn't see this part and you were only looking right here, what could you tell me about the trend going from sulfur, so hydrogen to sulfur to selenium to tellurium? So if we look at the periodic table, we've got sulfur to selenium to tellurium. As we go down the periodic table, what can you tell me the trend is? What are you noticing? The boiling point is increasing. Okay, so we can see that the boiling point is definitely increasing on there. Okay, but then if we take a look, and it does work for CH4. So if we look at carbon, silicon, germanium, and tin, so let's take a look again. So we've got carbon, silicon, germanium, and tin. It goes in the correct order, increasing boiling point. But if you look, when we've got hydrogen with oxygen, fluorine, and nitrogen, so this is oxygen, fluorine, and nitrogen, which is our phone, you can see that it goes outside the trend. Okay. And so what they believe, what the scientists have basically come to theorize, is that there must be something stronger, and that something stronger is what we call the, I see you saying it, the what bond? The hydrogen bond. Perfect. Okay, and so that's the IMF. What's the proper title of this graph? Remember that you always do up and then down. So it's Y versus X. So this would be what versus what? Temp versus period. Which three substances have the highest boiling points within their group? So we can see that oxygen, fluorine, and nitrogen. What's the strongest type of IMF that's found in those? Hydrogen bonding is the strongest of those. Okay. All right. So we've got electrostatic forces. These forces occur between charged species. They're responsible for the extremely, what is true of ionics? Their melting points and their boiling points are much higher, right? And so this is due to electrostatic forces. Ionic substances are not supposed to have IMFs, okay? Because those are between molecules and they're not molecules, all right? I have seen multiple choice problems where it'll say, what type of IMF exists? It's an electrostatic force. It's not an IMF, okay? So just keeping that in mind. examples, salt, even like silver. So even if you have metals, so you can have like a metal substance, those also have electrostatic forces as well. So this one's ionic with the sea of electrons for the metals, and then the ionics, remember, are going to be the transfer of electrons. And then this is just going to show what type of IMF do you think exists? So if you have F2 and it's nonpolar, tell me your IMF. What do you think? London dispersion forces. Good. NO is polar. What type of forces do you think are there? Does it have London dispersion?
Yes.
Yes, it does. Perfect. What else does it have? It also has dipole-dipole. Very good. It's also going to have DD. What about, does it have hydrogen bonding? I'm seeing oxygen, I'm seeing nitrogen. No, why not? There's no hydrogen. You need hydrogen for hydrogen bonding. Okay. What about HF? Does it have London dispersion?
Yes.
Yes. Does it have dipole-dipole?
Yes.
Yes. Does it have hydrogen bonding?
Yes.
Yes. Awesome. Okay, so it's going to have, all three of them. Okay, CH3OH. Don't forget, this is not hydroxide, not OH minus. That is not OH minus. That is not an ionic compound, okay? So that's methanol, which is actually going to be, we'll talk about what the, in this case here, we're going to have the carbon in the middle, and then we're going to have the H's with the OH going around. So, and it's polar, it's telling us it's polar. Does it have LD forces? Yes. Does it have dipole-dipole? Do we think that there's any hydrogen bonding?
No.
So we've got this, and it's not hydroxide. That is not ionic. That's not ionic. Is there going to be an electronegativity difference at all between the O and the C? What do we think? Is it polar? Yes. And is an oxygen able to connect with another hydrogen of another molecule? Probably. Yes. This is going to also be hydrogen bonding. Someone's going to have hydrogen bonding. Then we've got calcium metal, and I want you to see the jump here. LD forces? No. No dipole-dipole, not hydrogen. What kind is this? Electrostatic. So now we've got electrostatic with our sea of electrons, and this is also going to be electrostatic. I want you to take a look at the difference in the boiling points here. Our molecular weights are about the same. When you talk about, those are pretty much the same. Those are not really changing. But take a look at what's happening to our boiling point. Boiling point is increasing. And the reason why is all based on their IMFs. Okay, so that's just kind of summarizing that. All of them have similar formula weights. The stronger the IMF, the higher the melting and the boiling point will be. Okay, and so now all substances have LD forces, additional dipole-dipole for polar molecules. Hydrogen bonding is a special case, and it gives the molecules the highest boiling points out of those. And then we know that the weakest, we said, were London dispersion. Then comes dipole-dipole, and then comes hydrogen bonding as the strongest of those three. And then it just says, any molecule with a permanent dipole will undergo dipole-dipole intermolecular bonding, like CH3Cl. And so we can see where those dipole-dipole forces are going to exist in between those. Okay. All right. Last thing is called an ion dipole. And all an ion dipole is, for example, if you have something like NaCl, which has a positive charge, and Cl has a minus charge, what can happen is water can get in there, and you can get an ion with a dipole moment molecule. So since chlorine is negative, what part of the water molecule is going to probably attract to the chlorine? A hydrogen, because the hydrogen is going to be positive, right? So what happens is you get this right here between the chlorine and the water molecule, this partial positive here with the dipole, and this is called the ion dipole. So in case you see that, it's not made up, it is an actual choice. So just in case you get that. All right, I hope you enjoyed this quick little run through of IMFs, and happy day.